So we will now discuss the concept of index notations. This notation is very useful in simplifying the mathematics of mechanics and is widely used. So let's understand what it is. If you have your coordinate system as, say, x1, x2, x3, okay, it would be e1, 2 hat, e3 hat. This is your frame F. You denote the coordinates x, y, z, the components of a vector ax, ay, az, vector a, and the vectors itself, the unit vectors as x1, x2, x3 or xi, where I can go from 1 to 3. You can also write this as ai, where I will go from 1 to 3. You can also write it as ei hat, where I goes from 1 to 3. Okay. So if you have a vector a at any given time, based on this coordinate system, you can have this a1, e1 hat component. You can have a2, e2 hat component, and you can have a3, a3 hat component. Okay, I'll just remove this. Okay. So this is what the summation is. Just replace x, y, z by x1, x2, x3, ax by, let me just write it in full, a1, a2, a3 or ai, and similarly I hat, j hat and k hat as i1, e3 hat, I hat. Okay. So this is the convention. Now we also have this, that there is a summation over repeated index. Okay, so normally I, j or whatever index you use will always go from 1 to 3 in 3-dimensional. In 2D it will go to 1 to 2. So if you have dii, now see that there is a repeated index I over here. Okay, so that means you have to sum it over. So this will become d11 plus d22 plus d33. Similarly, if you have aj, bj, the repetition is over j, and you can write it as a11, a1b1 plus a2b2 plus a3b3. Similarly, you have, say, now vectors ei hat dot ei hat. That would be e1 hat dot e1 hat plus e2 hat dot e2 hat plus e3 hat dot e3 hat. This, as you know, will become equal to 3 because e1 dot e1 will be 1, e2 dot e2 will be 1, and e3 dot e3 will be 1. Okay, let's see how a vector can be written. So if you have a vector a at any given time, like this one in this figure, okay, it will clearly be written as a1 of t a1 hat plus a2 of t e2 hat plus a3 of t e3 hat. Okay, this can be written using the summation which we have just seen. Let me just write it as summation of I equal to 1 to 3 ai of t ei of hat, or in shorthand notation ai ei hat. Okay, here because there is summation, repetition is over I, so it will be summed over. So if you have, say, the position, so if A represents the position of a point, okay, that would be x1 e1 hat plus x2 e2 hat. Let me just first write out in our Cartesian form, plus zk hat. This, as you know, in index notation is written in x1 e1 hat plus x2 e2 hat plus x3 e3 hat. This is equal to I equal to 1 to 3 xi ei hat, or just xi ei. Okay, so now let's see some other examples. For example, if we have been given that bi is plus dij cj is equal to ai, you see there is a repetition over j. You have to only see the repetitions in the product, not in the summations. Okay, everywhere which you see the example, there is no, like, you cannot say that I and I are repeated index, that's not there. Okay, so there is a repetition over j. This would imply that this is equal to bi, sorry, bi plus di1 c1 plus di2 c2 plus di3 c3 is equal to ai. Okay, now this is an equation in I. So for I equal to 1, this will become what? b1 plus d11 c1 plus d12 c2 plus d13 c3 equal to a1. For I equal to 2, it would become b2 plus d21 c1 plus d22 c2 plus d23 c3 equal to a2. So for I equal to 3, since I could have taken 3 values, okay, both I and j would have taken values from 1 to 3, that's why we are doing this. Okay, so over here I is a non-repeated index. Okay, it's also called a free index. And j is a repeated index. Is a repeated index, and it is called a dummy index. Okay. Now we also call it dummy because you could have replaced j by any symbol. For example, if you had written this as bi plus dik, ck is equal to ai, you could have just got the exact same thing. Okay, because k again would have gone from 1 to 3 and the same result would have been arrived. So please verify this. Okay, verify that if you have k or l or p in terms of j, you would get the exact same equation. So as a rule, no index is permitted to occur in a given term 3 or more times. For example, AII cannot happen. BI plus DIJICJ equal to AI is not possible. Sorry, it is possible. DIJJCJ is equal to AI. This is not possible. Okay. So that's the summary of index notation, and there is also one other important version called the Kronecker delta. Kronecker's delta ij. So this is equal to, if I is equal to j, it is equal to 0 if I is not equal to j. For example, delta 1 1 will be equal to 1, delta 1 2 will be equal to 0, delta 3 3 will be equal to 1, delta 3 2 will be equal to 0. Okay, this delta ij also shows the dot product between the two unit vectors along directions. For example, ei dot ej dot is very commonly written as delta ij. Why? Because e1 hat dot e2 hat will be equal to 0. e1 hat dot e1 hat will be equal to 1. Similarly, e3 hat dot e3 hat will be equal to 1, and e3 hat dot e2 hat will be equal to 0. Okay, so this Kroneker's delta is also used to show this particular dot product. So you will realize that this index notation, this repetition over this summation, actually simplifies a lot of the mathematical analysis for us, especially when it comes to differentiations. We'll see that as the time comes. Okay, hold on, let's just move it. Okay. So we'll now also define the so-called degrees of freedom over here. Now is a good time to do that. So this is defined, okay, Remember the very first lessons of this course, okay? The meaning of defined. So degrees of freedom is defined, so let me say degree of freedoms of a mechanical system is defined as a number of independent parameters or the coordinates which are needed to specify its configuration at a given time. Okay, so you can consider a case in which you have a degree of freedom of a point in moving in 3D space this will be 3 because it can be specified by these 3 coordinates x, y, z or x1, x2, x3. One point which I should have mentioned when I discussed the index notation is that I, j, k, this system which you have is not just used for the Cartesian coordinate system, okay? It can also be used for the cylindrical or the spherical coordinate system where for example 1 r theta sorry r phi z will be given by x1, x2 and x3. Similarly for r phi theta it will again become x1, x2 and x3. Okay, and E1, E2, E3 remains the same. For example, this would be ER, E theta or E phi and EZ. So it's applicable to all the coordinate systems, not just the Cartesian. Okay. So the degree of freedom of a point moving in 3D space is 3 because it can be specified independently. Okay, it has to be independent parameters. I have underlined this already. Degree of freedom of a point constrained to move on a given surface is 2. Okay, so you can denote it by these two surface coordinates, okay, where this can be say in an xy plane or yz plane or zx plane, whichever you would write. Similarly r theta plane or rz plane. Okay, so these two symbols denote a general space configuration. Again, a point constrained to move on a given curve. This, as you know, is 1. Okay, the path coordinate. Yes, so this is the only independent parameter or coordinate needed. Okay, so that's the important part about this, that it has to be an independent parameter. So let's now see some more examples of this degree of freedom. So I should write this. Okay, let's see the position of a rigid body of a rigid body is known if the positions of any of its three non-collinear points OAP are known. So if I can draw, okay, so let me just draw this 3 points O, A and B. Okay, these are three non-collinear points, and if these positions are known, let's call this as B, let's call this as A, then I know the position of a rigid body. Okay, because any point in that rigid body, for example P, okay, this can be written in terms of some fraction of A or A and B. Okay, so if this is, sorry, this should not be here, let's call this as B, this is A. Okay, so then any point P of this rigid body can be known in terms of A and B. For example, this distance can be A by 2, this distance can be B by 2, 2B, B by 3, whatever, and hence you would know any point of the rigid body. And since all the points are known, then you know the position of the rigid body. Okay, you can also have this vector over here, it will be called A cross B. Okay, this is something which you already know. So you have A is equal to OA, B is equal to OB, and A cross B determine the coordinate system attached to the body. This implies any point is known. Sorry, not any point, the position of any point. Okay, because we are writing the position coordinate. Okay, now to define these locations O, A and B, okay, we would individually need 3 coordinates for O, x, y, z, 3 coordinates of B, x, y, A, and 3 coordinates of B. Okay, so total 9 coordinates to specify the locations of OAB. Okay, and you know that if OAB are located, then the position of a rigid body is located. Okay, but these 9 coordinates, are not actually independent. That's the important part. I mean, individually xyz of A and individually xyz of A, xyz of B and xyz of A are all independent, but because this relationship has to exist, it's non-collinear, and the vector A cross B cross A cross into B will define this coordinate system, then you can say that they are no longer coordinate, okay, no longer independent. Okay, these 9 coordinates are not independent. There are 3 relations, or the so-called constraint, imposed by invariant distances OA, AB and OB. Okay, so you have to now write these 3 constraint equations. Constraint equations. Okay, to see this yourself, what you will see is that the x and the y and the z coordinates of O, A and B are not independent of each other. This implies that only 6, and by invariant distances we mean these distances will not change in any frame. Okay, that's the meaning of this invariant distances. There are only 6, which is equal to 9 minus 3 independent coordinates out of 9 coordinates. Okay, so 6 is the degree of freedom, and what are they? They are 6 is equal to translation plus rotation fixed point plus a general motion. So for a rigid body you have this. These are the possibilities. Okay, you have to identify given in which condition what should happen. Okay, so the motion is called the motion of rigid body. Is translation if have the same displacement in F, or its orientation remains fixed. You can take a pen in your hand, okay, and try to translate it along the x, along the y, and the z direction, okay. Then it would be called a Orient translation, okay. This is also equivalent that the orientation is fixed. The orientation of your pen is fixed in F, okay. So this is a translation. You can also say there's a rotation about a point. This is obviously of a rigid body, okay. In F, clearly, if one material point of the body occupies the same location in F at all time, okay. This would again be degrees of freedom equal to 3. Take your pen, hold it at one end, okay, and then first try to rotate it around this in the xy plane, then try to rotate it in the xz plane, and then try to rotate it in the yz plane, okay. So you can have this rotation about a point which is your fixed point, and if one material point of the body occupies the same location, which is that material point of the body which occupies the same location? It is that point which you are holding with your finger, okay. So, and clearly in this case the rotation is also about that fixed point, okay. So this is something which is easier to visualize, and clearly there are 3 degrees of freedom because there are 3 possibilities which you can do this rotation, just like there were 3 possibilities of translation along the x, along the y, along the z direction. So you have a particular case of this rotation about a fixed line one degree of freedom in F, in which all material points of a body in this line undergo any displacement Okay, so you can just think about a tightening of a screw. The line over there will be the midline inside the screw. Okay, the axis basically of this. So if you tighten it, there is a rotation about this fixed line in which all material points of a body in this line do not undergo any displacement. So that can also be the fan, for example. Okay, let me take that's a better example. So fan, rotor. Okay, so there is rotation about the middle, the axial line of the rotor of the fan, and you can see that the material points in this line will not actually change. Axial midline. This is clearly degree of freedom 1 because you require only one variable, okay, to define this about it. One of the things which you should notice that this is a particular case over here, okay, a particular case of a rotation about a point. It's not a new possibility as such. I think the screw example should come now, which is slightly more involved than the previous one. That's called a general motion. So remember that we had three situations, right? Where did we write it? There is translation, there is a rotation about a fixed point, of a special case of which is about a rotation about a fixed line, and then there is this general motion. So I think the screw should come in over here. So a rigid body is said to have a general motion relative to F if its orientation changes relative to F. So this is clearly not translation, right? Because the orientation is changing relative to F. In translation, the orientation was not changing. And not or, okay? And both of them have to be true. There does not exist any point in it or on its rigid extension. Remember what a rigid extension was? It was a massless extension. Or on its rigid extension which remains fixed in F. Okay, this was a case, if you remember, rotation about a point. So it's neither translation nor rotation. Okay, and how can we visualize this? The motion of a nut on a fixed bolt. So bolt is a kind of screw, okay, but when you say nut always goes with a bolt. So in this case you have this bolt which is fixed. These are the threads of this bolt, and then you have this nut. Okay, so this will keep on rotating, And what is the general motion here? It's clearly not of the bolt, okay, bolt which is fixed. We can see that it's the motion of a nut. So the nut will keep on moving ahead in this direction, and it will also keep on rotating about this particular axis of the bolt, and this axis of the nut also the same axis. Okay, so you can see this arrangement, and over here there is the orientation will continue to change clearly, okay, because it is rotating, and then there will not exist any point on this nut or its rigid extension which remains fixed in F. Okay, so all the points of this nut are actually rotating and translating. So both of them cannot be identified either as a pure rotation or as a pure translation. That's why it's called a general motion. Okay, so I hope you can clearly understand this. So we must mention two important theorems over here. One is the Euler's kinematical theorem, an arbitrary displacement of, a rigid body with a fixed point is equivalent to a single rotation about a certain fixed line through that point. The other is the Chasles theorem, the most general displacement of a rigid body in spatial motion, meaning 3D motion, is equivalent to a translation followed by a rotation. About some base point and vice versa. What you have to do now is that you have to visualize, sorry, okay, you have to Why not get to get it? Hold on. Visualize this for motion of a nut in a bolt. You have to find what that sorry that it is you have to visualize that the most general displacement, okay, is that clearly of the motion of a nut in a bolt. Okay, it is equivalent to a translation. You have to see what is the translation followed by a rotation about some base point. What is that base point? Okay, similarly you have to visualize this, the Euler's kinematical theorem, that an arbitrary displacement of a rigid body with a fixed point is equivalent to a single rotation about a certain fixed line through that point. Okay, or other examples, whichever examples you can think of, as many as you can think of would be better over here. So we will now discuss about the angular velocity of a frame M, which is relative to a frame F. Okay, so let's see. You have to now recall the basis vectors ER of t and E phi of t. Okay, this was in the cylindrical coordinate. Now to find the angular velocity of frame M relative to frame F, we are looking basically for a concrete definition, that if there is a vector defined with respect to frame M, what would be that vector defined with respect to frame F? Okay, so you have a frame F and then you have another frame M. Suppose there is a vector defined with respect to M, what would be that vector A with respect to F when M is rotating, okay, or moving around? So that's what we are trying to answer. So let's define some of the things which we would need. You have the basis vectors. That means that any vector in this Cartesian, cylindrical coordinate system can be defined using ER, E phi and EZ. Okay. Okay. Consider a frame M to which ER hat, ET hat here at any given time. Let's also bring time into the picture. ER hat, E phi hat, EZ are attached. As you can also see from the notation that ER and E phi change their orientation with respect to F through phi of t, but EZ does not. So you have vectors I hat, j hat, k hat embedded in frame F. K hat. Okay. Let's see a constant vector. Any constant vector, displacement, velocity, acceleration. But constant vector means it is constant in magnitude and direction. A constant vector A in frame M its components will be what? AR, A phi, AZ are constant. That would mean that A of t would be AR, AR of t, okay? As AR, A phi and AZ can not be a function of time because they are constant. A phi of A phi and AZ now if you differentiate this with respect to time and observe this rate of change with respect to the frame F, one should get AR ER hat dot plus A phi hat dot plus AZ EZ hat dot. Okay. Now since E of Z is not actually changing with time, this particular term would be equal to 0. Okay. So we can write this as AR and then ER dot, if you remember, was, let me just check, we had derived ER dot sorry. Yes. According to equation 1.14, ER dot was equal to ER dot with F, okay, was phi dot E phi hat plus A phi, and E phi dot was minus of phi dot ER hat. Okay, so this can be written as AR phi dot E phi of t minus A naught phi dot ER of t. Okay, this was according to equation 114. Please go back and check this. Okay, now this can be written as phi dot Ez cross AR ER t plus a phi e phi e phi t plus az ez of t. Okay, so z cross z would be 0. Okay, z cross r would be phi, and z cross phi would be minus er. Okay, that's why this can be written. This can be written as phi dot ez into, what would this be? This would be a of t. Okay, and this can be written as omega of t cross for all a. Okay, for all vectors, obviously constant with respect to m. Now clearly where this omega of t is equal to phi dot of t ez hat is a measure of the rate of change of orientation m with respect to f. This is something which will go in blue, I think. We shall establish. I'm writing it in blue so that later on you can your attention can be drawn to it when you see this next. That this is a special case, particular case any motion of m in which omega need not be the derivative of a finite angle of rotation. This is something when it comes you will be able to see. So let's take that case of a general rotation now. Okay, let's see that what we have written in blue. Okay, the general rotation, the case general rotation of frame M relative to frame F. Okay. Now let's draw a figure. That's frame F. E1, E2, E3. Okay. Then have this frame M at T. There you have E1, E2, E3. This point is B. And of course, if you may have a next instant in which this becomes okay, it should actually be shown with a dotted. This is M at T plus delta T. So then this B would be T plus delta T. You would have E1 T plus delta T. You would have E2 T plus delta T, and you would have E3 as T plus delta T. Okay, so EI is fixed to F. The capital EI, as you can see, is fixed to F. The small EI is fixed to M. You can see that. Okay, the rate of change of orientation of M relative to F at given time t. Let's see how we can write that. So EI is fixed to F. EI is fixed to M. Okay, the rate of change of orientation of M relative to F change of orientation M relative to F at time t is governed by clearly EI at with respect to F t dot. Okay, that's the rate of change of orientation M relative to, because EI is fixed with M. Okay, so this time derivative with respect to F will give you the rate of orientation of the frame M. You can imagine that in a whole mechanism, this M can be a rigid body which is moving with respect to F frame. Okay. Okay. And these are not independent, like E1 dot may not be independent to E2 dot. So let's see how we can show that they are not independent. Okay, so EI dot EJ is equal to delta IJ. We have just seen that when we were discussing the index notation. So if you differentiate this with respect to time, one would get plus EI dot EJ with respect to F, because it's a time derivative, and this is equal to 0 because delta Ij is either equal to 1 or equal to 0. In either case, it will only be the derivative of that will be equal to 0. So this would imply that EI F dot time dot ej time is equal to minus ei time dot ej dot is equal to f, and this is equal to time. Now how many relationships are actually over here? See, I can go from 1 to 3, j can go to 1 to 3, but this is actually, and you should verify this, verify that these are 6 relations in all. Okay, you have to exclude the ones which are repeating, so please write out those 6 equations and see for yourself. Don't skip this stage, please. Okay, so this is called equation A. Sorry, this should be in black, and so you can write out that sorry, let me just change the color of this one to black. No. Okay, so this is called equation A, which will be used in a few minutes. Then you can write AI of t cross f dot let's just put this is equal to dot minus a t dot ei f with respect to time ai t. This can be called equation B. And how can it be written? Well, this is just a vector triple product. So you have, for example, A cross B cross C. This would be A dot C B. Okay. So does it satisfy? Yes. Okay. I mean, a dot c can also be written as c dot a. And this can be written as c dot b. But other than that, it's the same. Okay. So this has been written because of this vector triple product relation which we know. Now let's consider a constant vector in M, okay, and see that what we had written in blue over there can actually be shown. So consider a vector A is equal to AI hat in M, that is all AI are constant. Okay, that's the only way this will be a constant vector. So let's see if we can write this A is equal to this, okay. So we have A t is equal to AI EI of t. Now we want to take a derivative of this, find the rate of change of this vector A with respect to time in terms of frame F. Okay, that would be like this. Now if you apply the chain rule of differentiation over here, all the AI dots will be 0 because AI dots are constant. So that would only leave us with this. Okay. Now if your vector is this, what would be AI? AI would actually be A of t dot EI hat and EI hat time. Okay, so for example, if you have A, this is equal to AI EI hat, and you take A dot EI, you would be left out with EI AI. Okay, and that is not surprising. I'll just show it to you in an expanded form. You have A1 E1 hat plus A2 E2 hat plus A3 E3 hat. Now if you take A dot E1 hat, this would be equal to A1. A dot E2 hat, that will be equal to A2, and A dot A dot E3 hat will be equal to A3. That's why combining this we can say that A dot EI is equal to AI. Okay, so that is what exactly we have used over here. So this should also actually be done. Okay, now we want to use B. Sorry. we want to use this one. So where do we get? We want to get this particular term. From B we can write A1. Oh, sorry, not this term. I think it's the first one. This particular term. Okay. So we can let me just pull it down slightly. Okay. So we want to use from B this term. So now this will be replaced. That should give us EI of T cross EI of F, all with respect to time, needless to say. We are writing time just so that we don't really forget that there is time. Otherwise, if we stop writing, we often tend to fall off. Okay, so that's there. Now the second term would be this term. EI. Okay, that's easy. Now let's see EI of T cross EI plus EI dot. Okay, so this particular A of T has been again written as AJEJ, okay, because A was equal to this AIEI and I is a repeated index, hence it is dummy, so I am just using J over here. The reason is I don't want to confuse with this I over here. That's the reason for using J for this case, okay. Okay, so once this is sorted out, we can write this as EI of T plus EI of T cross A of T minus, okay, so AJ, let me just remove the J because J is a scalar, okay, so I'll be looking at this dot product. So I would have AJ, sorry, AJ and EJ dot EI dot, okay, EJ dot EI dot is actually equal to minus of EI at EJ dot with respect to F, okay, EIT. This is because of A. over here if you look at A, you will be able to find this one. Okay, so that's the property which we have just used. So let me write that out slightly nicely. This is equal to T cross minus EI dot EJ dot FT EJ EI T. Okay, now I use this relation again. Which one? This one. Okay, I use this relation. Let me call this C. Use C. Use A. Okay, this would become EI of T cross EI of F dot T cross A of T minus EI hat dot A dot of time EI of T hat. So this particular thing has been written as A dot with respect to F using C. Okay, and if you remember, this was actually, I'm sorry, this was a dot over here. Okay, so this was actually equal to A dot F with respect to time. Now I want to write this as equal to A dot F. Okay, and if that is true, then this A dot with respect to F will go on the left hand side, and we will have A dot with respect to F at a given time will be equal to half of EI of T cross EI of F T cross EI of F T cross A of T. Now let's see how this is equal to A dot. Okay, this should be, I'm writing this in some other ink now. Let me take a green. Hold on. So we want to show this term in blue. Let's see how we can do that, and actually I'll just use it for any vector because A dot will be a vector. So let me just use any vector, I don't know, V. Okay, and this, if I do this, will be equal to V. So clearly if you use the index notation, you will get a V dot EI and EI hat. This will be equal to V dot E1 hat E1 plus V dot E2 hat E2 plus V dot E3 hat E3. Okay. Now if your vector V, this is, if your vector V was actually equal to V1 E1 hat plus V2 E2 hat plus V3 E3 hat, then V dot E1 will become V1 E1 hat plus V dot E2 will become V2 into E2 hat plus V3 E3 hat, and this is equal to V. Hence we can say that this quantity will actually be equal to vector V, and that's why this is written like that. Okay. So we have seen now the derivation of this equation, which is equation, let's say equation T. Okay. Sorry. So where did it go? Okay. Okay. So we define this, again the word define is important, the angular velocity omega m of f of frame m relative to f at time t in terms of ei dot f t by this quantity essentially. Okay, so I'll just write it over here as omega of t, I'll just remove this, is equal to half of ei of t cross ei of f t. Okay, this is equation 1.47, and you know what this means in the expanded form. This would mean that it is E1 hat of time cross E1 hat dot f with respect to time plus E2 hat of time cross E2 hat of f dot plus E3 hat of time cross E3 of f t. Okay, so by this logic you can say that so you can see that how this quantity omega is actually a measure of the rate of change of orientation of m. Okay, so all the three rotations are possible. Well, in some cases, for example, E3 dot is 0, then you just take it as 0. Et dot is 0, you take this as 0. Okay, and on the other hand, if E1 dot, E2 dot and E3 dot are all 0, then it means that the frame is not rotating, or there's no orientation which is changing in M. Okay. So all constant vectors in, so you have to look at this equation that would show that all constant vectors A in M, there exists for all, there exists a unique omega of t such that A dot F is equal to omega cross A. This is a very, very important relation, especially when it's valid for any constant vector in M. Okay. Now if you want to visualize this, this is the way to go. If you have this constant vector A with respect to t, and then clearly it will have a A1 component, it will have a A2 component, and it will have a A3 component. So this is the components in the F system. Now in the M, they look like A1 of t, A2 of t, and A3 of t. Okay, and there will be clearly a change in rotation. So if you have B over here, this is a frame M, you have E2, E3, and you will then have E2 dash and E3 dash. Okay. So I hope this visualization is clear. Please relate the capital A's and the small a's. Okay. Okay. In particular, the constant vectors EI in M are EI of F is equal to dot 149. Okay, so since A could have been any vector, so let it be EI. Okay, and EI dot with respect to F will be equal to omega cross EI. This is also something which is very important and very useful. So let's now move and see the consistency of the definition of M. Okay, proof of consistency of definition of omega. So we will be referring to this figure, okay, this one, where E2 dash and E3 dash are given, and then you have another, I'll draw it clearly again, okay. Let me just draw that. And then let's take this point D. Okay. So you have E1, E2, E3 and E1 dash, E2 dash and E2, E3 dash. Okay, let me just consider. So clearly this is B, this is M. Another orthogonal meaning all the three axes are perpendicular to each other. Right hand unit triad EI dash fixed to M. This implies EI dash are constant in M. Okay, so EI dash are constant in M. Let omega be equal to omega I EI hat or omega I dash EI dash. Okay, this I hope you can understand. Perhaps I have discussed it, perhaps I have not, so let me just do that here anyways. You have any vector in the I and j coordinate system. Okay, let that be, let this be rotated, say, I don't know, let this be r is equal to xi xi plus yj. Okay, and the same vector can also be written, let me draw a new one. Say you have another I dash and j dash coordinate system. The same vector can also be written as x dash I dash plus y dash and j dash. Okay, using another coordinate system. So the vector remains the same, but the basis vectors in terms of which they are defining is I and j over here and I dash and j dash over here. Similarly, this vector is omega. Here it is defined using E i's and here it is EI dashes. Okay, now omega dash will be equal to half into ei dash multiplied by ei dash by f. Okay, so how can this be written? This can be written because of 1.47. Okay, so if you go to 1.47, okay, you have omega is equal to half into ei plus ei dot. Similarly, you can write omega dash is equal to half into ei cross ei dash into ei dot dash. Okay, so this can be written by, sorry, this can be written by 1.47. Okay, and the other part, this equal to half into omega I dash, so this particular thing can be written by 1.49. Okay, 1.49 was the rotation of the constant vector ei. Okay, so please check these statements and verify that you have understood them. Now I'll write this as half into ei dash dot ei dash omega minus ei dash dot ei dash omega minus ei dash dot omega ei dash. Okay, how has this been written? This has been written because again there is this, we are applying the triple product rule over here. So A cross B cross C is equal to A dot C to B minus A dot B into C. Okay, so you can apply this and get to this stage. This should be equal to half into 3 omega minus omega. Okay, this particular thing we have already seen in blue, where uh, sorry, over here. Okay, this is what we have already seen, and the other part is somewhat straightforward. This is ei dash into ei dash, so that is quite easy. Ei dash dot, it is equal to e1 dot e1 plus E2 dot E2 this is 1 plus 1 plus 1, so that's equal to 3. Okay, so that's why you have a 3 omega, and this should eventually give you a omega. This implies that omega is independent of the location or the direction of EI in M. Okay, so it will, that's where this consistency of the definition of omega was being checked. Okay, so the omega is unique no matter where you attach your coordinate system in M, either the black one or the blue one, or does not matter how you orient it, like you can see in black and blue, the omega will remain the same because omega dash has come out to be equal to omega. Okay, so it is a measure of the rate of change of the location or rate of change of the orientation of frame M as a whole relative to the frame F. And not a particular line element in it. Okay, so now we can establish a general relation between A dot M and A dot F for an arbitrary vector AT. Let's see. We establish let me just do this now. I think I require more screen. So we establish the general relations between A dash between A dot of M and A dot of F for an arbitrary vector A of t. Okay, so let AI, So we had drawn that figure above, but we'll just draw it again, okay? A of t, A1 of t, A2 of t, A3 of t, A1 of t, A2 of t, A3 of t. Okay, so let AI t and AI of t be its component. Whose component? The vector A, okay? Its component along the capital EI. Remember, this was the system attached to F, and small ei. This was the system attached to M, okay? So A of t will be equal to AI of t EI, and it is AI of t EI. Okay, both of them represent the same vector. Now let's take the time derivative. A dot of f with respect to time is equal to A should go up, okay. I should write it as A dot EI is constant, okay, because EI being constant means that we are in the frame F, okay, and that would mean that it can only be A dot I EI dot hat, okay, because EI hat will be equal to EI dot will be equal to 0 since we are in this frame F. Similarly, A of M, A dot of M is equal to A dot, so the dot should be visible, such that the M coordinate system is fixed, okay. That means that this would be AI dot EI hat, okay. F is equal to AI EI hat, okay. So AI EI is written for F, and then there's a dot over F in time, dot over the whole thing. This would be, if you apply the chain rule, would be AI dot EI hat plus AI EI dot with respect to F. This will be equal to, using this one, okay, you can write the first term as A dot with respect to M plus AI into, now this particular thing can be written using equation 1.49, okay. 1.49 was that EI dot is equal to omega across EI, so that would be omega cross EI, okay. this would be equal to A dot M plus omega cross AI hat. Okay, we can just take this AI scalar inside it. Okay, not a big problem. Now this will be written as A dot with this. So this implies, I think now we are getting to it, that the rate change of this vector A in terms of the F frame is equal to the rate change of this vector in the M frame plus omega cross the vector itself. Okay, because this is the vector A. This implies that any vector F, any vector derivative, time derivative in frame F is equal to, sorry, not three signs, it's the same vector in respect to M into omega of M with respect to F, okay, multiplied by the vector itself. This is equation 1.50. It is needless to say that this term represents the change of A relative to F due to the rotation of M relative to F. Okay. So if you want to write the time derivative of omega mf, what would that be? So if you have omega dot f is equal to, what would it mean? D of omega m by f by dt with respect to f. Omega m by f plus omega cross omega. Okay, so here you could have put any vector, right? So we are putting omega over there, and this is equal to omega dot with respect to m, because this will clearly be 0. Okay, so this is 1.51. So omega, and it's the same, that's the important part. I mean, this particular vector will be the same whether you observe it in the F frame or the M frame, that rate of change of this. So omega dot is equal to omega dot with respect to F or omega dot with respect to M is defined as the angular acceleration of frame M relative to F. So Just to remind you that omega dot with respect to m is actually omega m with respect to f, the whole time derivative is with respect to m. This is not equal to omega m by m, okay, with respect to m, because this is clearly equal to 0. Now to find omega dot, there are three possibilities. One is that if these are the things which will be useful when you try to solve some problems of this course. When you have this is equal to omega I of t e I hat, then omega dot mf is equal to omega m by f. So this overhead bar I show just that the entire thing is derivative of time. Okay? Otherwise it's always a confusion. Dot is equal to ei dot ei, okay. Just because ei dot in the m frame will be 0, okay. That's why those terms are not coming up. Okay, sorry. Not so much. The second case would be that you have everything defined in the f frame. Let's see that. So if omega m of f with respect to time is equal to omega I of t e I hat, then your omega m with respect to f dot would be equal to omega of m with respect to f is equal to omega I dot ei hat, just because the capital ei dot will be equal to 0 in the f frame. And the last one, which is essentially neither of these, is that the omega of m f is t is equal to omega star of t, so this is capital omega, okay, ei plus omega star small ei, okay, then omega of m by f dot is equal to, sorry, so you have to take a dot over here plus dot ei hat plus omega m by f cross omega I star ei star. Okay, this is something which you should be able to verify by this stage. Here, let me. What you have to do is you have to use something like this, okay, or more 1.50. This one, don't leave it, okay. Please pause the video and only continue ahead once you have done this verification.